what I could do, let's say somebody's hacking it or something, and the hacker's coming from the IP address of, let's say 222.100. So let's say that's where the hacker is here, and his IP address is 222.222.1. Sorry, .100 actually. I select this text here. All right, let me just put 00 on the end. It's not letting me select that text for some reason or other. That's 100 there. So if that's where the attack is being sourced from, well, what I could do is I have a few options here. What I could do is I could filter the traffic so that it can't reach, so that it cannot reach the destination. But that's not going to be a good solution, because if I use that solution, if I use that solution, well, what's going to happen is nobody else is going to be able to reach that destination. If I filter the traffic as it goes out, the problem is if I filter traffic as it goes out, it's going to already go to the server, and then I'm going to hit it as it goes out the router here again. So as it goes back out the router, I could filter it here. But that's not the, that's not the best solution. The best solution would be able to hit it in the beginning. I could hit it in the beginning by putting an access list on, like right here, or an access list on here that says, okay, traffic from this source to this destination. But that's really a pain in the butt to put an access list on all the time. So what I'll do is I'll just put a route to null 0 for that source. And then what's going to happen in enable unicast reverse path forwarding. So then what's going to happen is when the packet first comes in, unicast reverse path forwarding says to check the source on this here. The source is the null 0, so it drops it when it first comes in. So it's like filtering without filtering. Just by doing the unicast reverse path forwarding, filtering, and the static route, we drop this traffic. So it doesn't require complex access list entries. If a server is under attack, you just drop into the router, put a route to null 0 for the source, and then it's dropped. All right. So the syntax here for the command, the two different modes here. Oh, as a side note, required for Ceph. Ceph is required for this feature here, I should say. Two modes. Strict mode here. The command syntax a little bit different. IP verify, unicast, reverse path. That means you must be coming, their traffic must come in the interface I would route to get to that source. Okay, I could have multiple routes to it, and then any of those interfaces are valid. The loose mode says I must have a route to you somewhere in the routing table other than null. Okay, if it's rather than null, you get dropped. This is the most common option that you see, because if you don't have routes to the RFC 1918 addresses, those packets are dropped. If you want to black hole some traffic, you just put a route to null 0. As soon as that traffic comes in with that source, it gets dropped. Any dark networks that aren't being, or actually should say, mostly the term is dark IP addresses that aren't really allocated out there, then let's say if you've got a whole bunch of /24s that aren't being used, if you don't have routes for those in your table, but yet your /29 or your /20 advertises those to the internet, as soon as that packet comes in, gets dropped. All right, a lot of times what people do in that case, let's say if they have a slash 29, but yet there's some slash 24s or something that's not being used of that. Sorry, not slash 29, but slash 19. So if you have a slash 19 or a slash 20, and then you have a lot of these slash 24s that you are not using, what you can do is on your edge router that has this feature configured, just ensure that it doesn't have a route to these slash 24s, and then it's going to drop it. What some people do, though, is they create these dark IP addresses, and essentially they have a machine that's got every IP address that isn't used is addressed on one machine. Then they just, it's like a sinkhole. They suck up all this traffic. So all this traffic gets sucked up. Another thing they do commonly on the edge is they'll just route this traffic for these unused networks to null zero. Just drop it right there. All right. But if you just enable this feature and you don't have a route, it gets dropped. Okay, so those are the two modes here. The one we're going to see again here coming up here is we're going to see loose. Okay, we're going to see loose because we're going to use it for some advanced filtering techniques. Okay, commonly disabled services we normally disable. Okay, for ISPs, Finger, BootP. You may see some other ones like TCP small servers, UDP small servers. Those are disabled. You may see one called PAD, which is X.25. You can actually communicate. You can actually manage a router through X.25, meaning that you can connect to their router remotely using this X.25 address. The command no service PAD in the global config, which is the default now, that disables that functionality. No IP BootP server, of course, the standard CDP stuff, proxy ARP, redirects, pretty standard. No IP directed broadcast, that is the default. I'll mention real quick, I'll talk real quickly about what a Smurf attack is and how it relates to this command here, but it's probably the most overblown attack that you see. And it's, I don't know, it's like every practice lab you ever see has got something, it's got, any security one has got something to do with Smurf attack, but we'll talk about it here. No IP unreachables under the interface. Okay, it's changing, it's saying do not send ICMP type 3 destination unreachable. Also, the router by default rate limits these. It'll send 1 per 500 milliseconds. That's like sometimes when you do trace route. Trace route, and you get these, you get these stars in the path because maybe this destination isn't reachable there. You can also do a ping to an IP address that the network is advertising for, an IP address in a network that router is advertising, but yet the IP address isn't actually assigned. That would be another way to test this here. These type 3 unreachables here. So it's quite common to rate limit these. The iOS rate limits these by default. Why? Because if not, the router will become the target of a denial of service attack. You just send, a bunch of packets to destinations that are not really assigned. And the router's got to generate all these. This person's got to try to ARP for it. Then it can't ARP for. Then there's no reply. Then it sends back these unreachables, and then it just you create a DOS attack to the router itself. And that's essentially what happened. I don't know if you guys remember back in about 1997 time frame, back when the day when people would DOS Yahoo or E-Trade, they would DOS these major websites. Then they eventually fixed it. The next step they went after is they DOSed the routers. The routers were the ones going down. The way, like E-Trade, the way they dealt with these DOS attacks, they just put bigger and more servers up. There's so many servers distributed around different locations. There's so many of them, and they're so powerful, you just cannot overtake them. It doesn't matter. You can overtake a small site these days, but you can't overtake like Yahoo. They just put more servers up, different locations, and I thought that was actually kind of interesting. I thought there would be some really cool technique they were using. No, it was just so many servers that were so powerful that you just couldn't take them down. Then what they started doing, people trying to do the DOS attacks, they started hitting the Cisco routers in front of them. All right. Luckily, though, that didn't make it to the, some of these times when these outages happen in the late 90s, 97, 98 time frame, sometimes these outages happen. It wasn't Yahoo going down. They attacked the Cisco router in front of it and then essentially brought it down. Okay, so the router, like I said, this is on by default, defaults to 500 milliseconds. You can change that behavior there. Quite common to change it in an ISP environment. Maybe let it send one every, 3 seconds. 500 milliseconds is one every half a second, and that's the default value here. But it relates to these, no IP unreachables. If you're routing a packet to null zero, normally you put no IP unreachables under the null zero interface. Okay. Real quickly, talk about a Smurf attack here. Basically, what you're doing is you're sending a ping to the directed broadcast IP address. Your source is the source of the device you want to attack. So what happens is you send the ping, an example would be you send the ping to 172.16.255.255. Okay, that is the destination. So that is the destination here. The source is the server that you are trying to attack here. Source is let's just say for the sake 1.1.1.1, which is the server down there bottom. This came out about 1999, 98. This started happening. I actually remember customers getting hit with this. I was working for Pacific Bell at the time. Basically, what happened is, they were just sending out these pings to the broadcast addresses. Tons of devices would respond. The source was the target, and they would all respond back to. They all respond back to the server. You think about it, it's just a way to amplify your traffic. That's all it is. RFC 2644, Cisco routers are compliant with. They say that you do not have this enabled by default. Okay. What they did is they came around this and they did a variation of this. They did what's called a Fraggle attack, and they sent a UDP echo to the directed broadcast IP address. So as soon as people started filtering ICMPs to the directed, they did UDP. So the difference of the two, one is ICMP based, one is UDP based. But the idea is you're just using the concept of directed broadcast so that you can amplify your traffic. You sending 100K to 100 users, and then they all reply to that bogus source. You can see all the bandwidth that the real source is going to end up with. Okay, a lot of times, when the internet was a little bit more wild, back when you only had about, 1996, had about 45,000 routes on the internet. It really wasn't as secure as it is today. Not that it is secure today, but it's definitely a little more secure. You're not going to have these devices normally be able to spoof the IP address. So you're not going to have this PC over here able to address, put any IP address on it once. Okay, it has to use some sort of protocol that's connectionless. Okay, it has to use some sort of protocol that's connectionless. So it uses ICMP or UDP. It really doesn't work with TCP because it's got to do a three-way handshake. So you can't really send you could send a TCP SYN possibly to a broadcast address, then the SYN-ACK goes back to the source, but it's always been connectionless protocols that it's using. But like I said today, most people don't allow traffic inbound unless it is address space that's allocated to them. So unless it's an address space that's allocated to them. All right, and this is on by default. No IP directed broadcast. It's on by default. It's been on a long time. But every now and then you see people, how do I mitigate a Smurf attack? Or how do I mitigate a Fraggle attack? You know, there's no IP directed broadcast. All right. I wanted to mention it here because for whatever reason or another, it's just one of those features that just create a lot of confusion. You can also stop it if you have to have broadcast enabled, directed broadcast enabled, and you need to stop it. You can use unicast RPF to stop it, because when this person over here sources, if it sources the packet from 1111 and this router doesn't have a route, if that's not the reverse path for 1111, if this router routes to 1111 out the internet here, so over this direction here, the unicast RPF check will fail and the packet gets dropped there. So it gets dropped by this router here. So there's a lot of things in place today to stop this kind of stuff. Okay. So black hole filtering. This is just standard black hole filtering here. Different ways to do black hole filtering. We talked a little bit about doing it based on, oh, real quick, somebody asked, isn't it usually a valid source? Yes, it is usually a valid source. I just used 1111 as an example. It's usually, well, and it has to be the source of the target. So the traffic would be sourced from the, whatever source your target is, that's what you want to use. If I have a vendetta against eBay, I'm going to source my packet from eBay's web server's IP address, and I'm going to send that ICMP echo, you know, with eBay's source IP address to, you know, the directed broadcast address. I just use these in here. Question said, meaning URPF would not work. But if eBay's IP address, if this router here, let's say this edge router over here, if this edge router over here had unicast reverse path forwarding on it, depends on the mode if it'll work or not. If it's strict mode, and the packet comes in here, but yet the router would route out here to get to that source, it would get dropped. If it's loose mode, if we turned off strict mode and went to loose mode, then when the packet comes in and goes to the router says, do I have a route to this destination or not? Yes or no. If I do have a route to it without any interface, the packet will get forwarded. So it'll depend on the mode that you're using unicast reverse path forwarding. In this case, if you only have one or two interfaces, you're probably going to do strict mode. If you have 5, 6, 7, 8, 9, 10 interfaces, you're probably going to do loose mode. It's where strict mode is usually applied on routers that only have one or two connections. If you start having multiple connections, that's when you really want to switch over to loose mode, and you pretty much change the whole behavior of it, too. All right. So black hole filtering, the basic idea is that we're going to forward this traffic to null, either the destination to null. If the server's under attack, so let's say the server's under attack here, what I can do is I can just forward that traffic to null right there on that first hop router. That's not a really good solution, though, but it is a solution. So I can forward the traffic to null on the first hop router. The traffic will be dropped. Another solution would be to go on to the router connected to the server and then traffic to that source of the attack, this PC source here. I could drop it right there, drop the source right there. This is all doing destination-based routing. So when the packet gets sent to the server and the server starts to reply back, I could drop it. Doesn't help for a DOS attack, but it helps against if somebody's hacking the machine. If I think somebody's trying to compromise the machine, then what I want to do is I want to somehow break that communication. If it's just a large denial of service attack, dropping the source after it comes back from the server is not going to really do you any good, because it's already hit the server. You're better off hitting it at the edge. What you may do is you may have multiple connections out here to the internet here. So you may have other routers out here on the internet, and then you've determined, on the edge of your network, I should say, but you've determined that the source of the traffic is coming through this router right here. So it's coming through this edge router. So what you can do is you can drop that router's route to the server. So okay, you may affect you may affect your customers that are connected through this here, but you're needing to stop the denial of service attack. All right, so how can you figure this out? Especially if it's like a some sort of TCP SYN DOS attack against the web server, it's not easy to figure out. You can do actually use features in QoS to help you try to figure it out. Possibly what you could do is, let's say your web server is under a DOS attack, but you don't know where the source of the DOS attack is coming into your network. So let's say this is your network here. So this is your network. You've got 3 edge routers. You don't know where this traffic's coming in, but you're getting a heavy DOS attack against this server. The customer's screaming to you, hey, fix this. I'm under a DOS attack. I'll tell you a really good example. Actually, here in Reno, I work with 2 ISPs. One of them hosts some online gambling sites. Right before the Super Bowl, they start getting all these requests from they're nothing more than essentially the mafia overseas, like in Eastern Europe, and they start blackmailing these sites. They say, if you don't send $10,000 via Western Union to us, we will bring down your server before the Super Bowl, because that's the biggest online sports betting time they have. So basically what's happened is both these ISPs will not host online sportsbook places. Nevada is the only place where you can do sports betting. And these 2 ISPs will not host them because of this. Because what happens is, of course, these websites don't pay, and then all of a sudden you get this big DOS attack, 2 days or the day prior to the Super Bowl, and starts bringing them down. But I thought it was really amazing. It's like you get this ISP. I consult with them. They call you up and they're going, hey, we've got these customers and they're being blackmailed. What can we do? And it's like, well, there's really not a lot you can do. You pay them off, maybe. The best thing to do is just to boot the customers out of the ISP. Here they are with some, $29 web hosting account, and they're going to bring down they're going to essentially bring down the whole network because of these 2 or 3 customers there. But yeah, so back to what I was saying was trying to find the source of it. So trying to find the source. Where is the traffic coming into our network at? Well, what I can do is I can go onto the edge routers, and I can mark the TCP SYN packets. I can mark them temporarily, and I can give them maybe an IP precedence or a DHCP bit marking. So I'll mark this one with 1. I'll mark this other one up here with 2. Actually, let me move this real quick here. So I'll mark the other one up at top with 2 there. And the last one over here I'll mark with 3. So this will be marked with IP precedence 1, 2, 3. Better off doing DSCP bits because you may already have some traffic already marked with IP precedence, depending on your situation. Then what you do is on the router outbound interface towards the server, the packets that have the IP precedence set and the TCP SYN towards the server, you log those packets. All of a sudden, you'll see this access list start going crazy, and it's because, okay, now you found the source. You can look at the access list that's being hit. Okay, it's this entry with this IP precedence, and you can match on IP precedence in an access list, and you can find where it's entering your network at. So you're essentially using QoS to quote unquote color your traffic so that you can find the entry point in your network. This is beyond the scope of the service provider lab, but I just mentioned it because most people here do work for either large enterprise networks or do work for service providers. But it's just a way of doing it on the edge here. But standard black, once you find the source, then you can go up and try the source, not only the source, but where it's entering your network at. You can try to communicate with that ISP, or if it's a company that you're connected to there, you can try to communicate with them to try to get them to try to find the source there. But it's definitely not easy, though. You're better off just dropping the traffic on your own than trying to deal with neighboring ISPs or companies or whatever there. Okay. So standard black hole filtering, we just get on, we put a route to null. More advanced standard black hole filtering would be use boost mode, unicast reverse path forwarding, and then do a static route to null for the source. If you know where the source is of your attack is from, you can use that method there. But we're talking about two types of attack, though. Keep in mind, one is a DOS attack, and then one is just somebody trying to scan your network and scanning open ports, looking for different vulnerabilities in PHP and Perl. This happens all the time. Okay, and those people you want to filter out. Quite common, you'll see a list of address space that's just blocked, and it's because the ISPs are constantly being scanned by these particular address spaces. Okay, so two different types of attack we're referring to. Obviously, dropping the source, if it's a big DOS attack, not going to do you a lot of good because it's going to be coming from a lot of different sources. Okay, so the black hole filtering, in this case here, we'd have to telnet to each router, apply this configuration to drop this traffic, and so forth. So if we found out the source was, 28.50.1.100, we can go and put a null route on each router for that towards that destination. The unicast RPF loose mode will drop the traffic for it there on the edge. So that'll mitigate that problem. The issue is, though, the issue we have is that we've got to go to each router and put on a static route for this, which, of course, does not scale. All right. So let's look at a solution that will work for us, that will scale. And it's called remotely triggered black hole filtering. Basically, the idea is that we want to remotely apply those routes to null, either for the destination or for the source, whatever we want. I mean, the route could be towards a destination or towards a source. So we want to quickly have a way to apply this policy or this requirement that we have to drop certain traffic. We want to quickly apply it without having to manually go onto all the routers, and we want to quickly be able to remove it too when we're done. Sorry, not when we're done, but when the attack is over. Because a lot of times it's a compromised server that's done it, so you don't want to filter it forever there. Okay, so remote triggered black hole filtering, it allows us to remotely do this here. So we are going to remotely do it, filter this, essentially apply force traffic towards null using what we call a trigger router. We can do it based on the source or destination, meaning we could drop traffic destined for a network, or we can drop traffic based on the source of the IP packet. And of course, if we're using source space, we know we're going to get back to the URPF feature, loose mode here. Okay, so the destination, what we're going to do, basically what we're going to do is we are going to pre-set up on all the routers a static route for a particular IP address to null 0. So we're going to say IP route 192.0.2.1 here as an example here. 255, 255, 255, 255, we're going to say null 0. So what we're going to do is we're going to put this on all the routers here. So we're going to say IP route 192.0.2.1/32 to null 0. Then what we do is, we advertise the route to the destination and set its next hop to this right here. We set the next hop to this right here. So we advertise like through BGP. Like under a route map, say set IP next hop or set next hop. And then what's going to do is when it's advertised across to the edge router, okay, to get to this destination, the next hop is this IP address, but the next hop is routed to null. So that's what you're doing. You're using the next hop functionality of the routing protocol to route the traffic to null. All the edge routers all have on one static route to null 0 for this particular IP address that you're going to use. So the IP address that you're going to use is going to have every router on the edge will have a static route for it. The same thing happens basically with the source filtering. What we'll do is we'll advertise the source. So the source of the packet, let's say if it's whatever the source is, we'll advertise it in BGP, set its next hop to this right here, 192.0.2.1. So we set the next hop to that. Then what happens is we have enabled on the interfaces loose mode unicast reverse path forwarding. So when the packet comes in, the router checks to see if it has a route to it. Yes, it has a route to it, but the route to it is via null 0. The next hop is 192.0.2.1 via null 0. So that packet gets dropped on the edge of network as it comes in. So you use the unicast reverse path forwarding feature to drop based on the source. The destination is just flat out routed to null 0. Okay, so but we're going to do this remotely though. So we're going to do this remotely on a triggering router. So basically the problem that we have here, this is like a distributed denial of service attack. We've got, some device activates all these zombie PCs here. One of them is probably Brian McGann's PC, who knows. And then they go down and attack the server here. So I'm just kidding. It's not Brian. It's not Brian's PC. And they've got that antivirus firewall stuff with AOL now. So they activate the zombie PCs. The zombie PCs all try to attack this server here. So they all try to attack this server right here. So in this case, not a lot we can do. We probably don't know what the source is, but what we can do is what we're going to have to do is on these routers here, we need to get in here and drop this traffic here. Yeah. Okay. No, I said Brian. I didn't say Brian was the person. I didn't say that Brian was the person being attacked. Someone said they liked Brian's red pants. It is pretty fancy for him, though. Brian's PC is one of those up the zombie PCs here. I'm just kidding. But so in this case, what we're going to have to do is we're just going to have to, these routers on the edge, we're going to have to drop it. We're going to have to drop it here. So we're going to have to drop this traffic. There's no other way to stop this. Assuming this is, not a big server like Yahoo or something like that, because you're not going to be able to, not say you can't, but it'd be really hard to do a denial of service attack against them. Okay. All right, so let's look at a way of doing this not automatically, but essentially doing it in one place and then it affecting all the other routers here. So what we're going to do is we're going to set up what's called a trigger router. So in this case, it'll be this router right here. This will be our trigger router. And what we're going to do on this trigger router, let's say the destination of the attack is, for simplicity's sake, let's just say 192.10.1.100. So this is the destination of the attack. So the destination of the attack here, 192.10.1.100. And the problem that we're running into, and this is the problem you have in the real world, is that it's not you that's under attack, but it's you being affected by it. Because this device is under attack, you're on the same switch, Ethernet switch, as this other web server. So all of a sudden, the DOS attack affects them because it's hitting them, but it affects you because you're on the same, Ethernet switch. Or you may be on the same server. You may be running virtual servers here. So what you may do is you may drop that traffic on the edge, people trying to get to it, just so your other customers aren't affected. Okay, it gives you time to Western Union those people the money. Just kidding. But yeah, you're going to drop this traffic right there on the edge here. So how are we going to do that? What we're going to do is we're going to set the next hop to this network here /32. /32 here. We'll set the next hop to null 0. Okay, so we're going to set the next hop to null 0. The way we do it remotely is on the edge routers. They all have the IP route. Make the font smaller real quick here. So they all have the IP route 192. The reason this IP address is chosen because this is a test network. 255, 255, 255, 255, and then null 0. So they have this static route on already. These routers do. All the edge routers have this preloaded. Now what happens is once this network comes under attack, what you're going to do is you're going to send a BGP update to these edge routers from the trigger router, and what you're going to say is to get to 192.1.100/32. The next hop is 192.0.2.1. So you send this BGP update, and you ensure that when you send the update that it is, you give it some sort of preference. In this case, it's a /32, so it'll probably be, you probably won't be getting a /32 from the internet from somebody, but you just want to make sure that the preference will overtake an eBGP route. So you send an iBGP route from the trigger router saying to get to this destination, go to this next hop. The routers are preloaded to say this next hop is via null 0. So what happens is this packet gets routed to null 0. So the packet gets routed to null 0 once the server's not under attack anymore. So once the server's not under attack anymore, you remove, you essentially remove this here. So you're going to essentially remove this here so that these other devices do not pick this up. Basically, the trigger router is going to use, we're going to look at the exact configs in a second, but the trigger router is going to use a static route. It's going to have a static route that's redistributed into BGP. So you can have a static route that says to get to 192.1.100/32, go to 192.0.2.1. Or you could put it to null 0, whatever, because in your route map, when you redistribute static in, you're going to say set IP next hop. You're going to set the next hop so that it is 192.0.2.1. So once the server's not under attack anymore, you're going to remove this static route. So then what's going to happen is remove the static route, they don't have this route anymore, and then the traffic flows on down. All right, but what you're doing temporarily while you have this trigger activated, you are pushing the problem back up to the edge. So now all this traffic is getting dropped at the edge of your network, not getting dropped or making it all the way to the server here. So let's look at the configuration here. So the configuration we have, this is the trigger router, it's the one we talked about here, and this is the edge router here. The edge routers, those are the ones on the edge. Somebody mentioned real quick, but doing this would take the server out of internet routing. Yes, but the problem is, like I said, the problem is if you get a server in the real world, when you get a server under a DOS attack, and let's say you're not working for a big ISP like some of these ISPs here in Reno, these aren't big servers. I mean, when they've got 300 clients on that server. So they got 300 clients on that server, and what they do is for customers that may be potentially open to DOS attacks, Anybody that does any sort of e-commerce stuff, they do IP-based hosting so that they can filter the stuff on the edge. Okay, yeah, they will get that server will go down, but the other servers will not go down. The other the other web servers on that same machine will not go down, because if you send 10 megs, into that machine, you may affect everybody else that's on that same segment too. The idea is to drop it at the edge. So yeah, it is a denial of service attack, and you are kind of helping it along by blocking the server, but you don't really have too many other choices. I mean, you can't get out there and tell all these people to stop. They may eventually stop, and when they do, you put them back. You remove that, but while they're under a DOS attack, because they're affecting other customers, if you have an OC3, and your DOS attack's taking up 20 megs of it, I mean, you want to go ahead and drop that stuff. All right, so yeah, you do block out the server temporarily, but that's just the way it goes. I mean, that's what you have to do. I mean, there's not too many other options besides put up, bigger servers, or put them on separate networks then. Okay. The edge router configuration. They have a static route to null 0. So they have a static route to null 0 here for this 192.0.2.1. Standard IP address. This is an IP address that's allocated in RFC 3330. I think it's 3330, not 3030. It's used for testing purposes. So what we're going to do, it's a non-routable IP address. It's kind of like RFC 1918 addresses, but it's not even private. It's just used for testing. So what we'll do is we'll put on this static route to null 0. The idea is that when we want to drop a route, we're going to send a route to the edge routers, and the next hop for that route will be 192.0.2.1. So that will be the next hop. Okay, like in this case here, we also put on no IP unreachables, pretty standard here. So when we drop traffic here, so on the trigger router, we have it. There's our neighbor statements here. So there's our neighbor statements. This is our neighbor statement. And in our case, in our case, R4. This would have been R4 as a trigger router, and this config would have been on R3 and R6. Okay. You have redistribute static and then a route map. So you redistribute static routes in, and you have a route map here. What you're doing is, just to be careful, you're doing a tag on the static route. So you're doing a tag on it, and then you're matching that tag so you don't inadvertently redistribute another static route in there. Usually when you redistribute static routes on a production network, you have some sort of route map that allows only certain static routes to go in, and the best way to do it is by tags. So that's what the tag has done, just to ensure that only this one goes in. We set the local preference. The reason the local preference is set so that we can we make sure we don't prefer an eBGP route. We want to ensure that the route we send is preferred, so that they don't prefer some other route. We want to set our local preference higher than everybody else. You may also want to do stuff like set community no export or set community no advertise. Okay, so this route doesn't leak out. Okay. So what we do is we redistribute the static in. We set its local preference higher than the default, so that or higher than whatever we're using, so that we make sure the edge routers prefer this route that we're going to send them. So we're saying the destination of the attack and the mask, whatever that is, either it's a whole network or it's one particular /32, whatever it is, and then we say set IP next hop to this. So when that edge router over there gets that packet is going to have a, let's say the destination in question like we showed here, 192.1.100/32. The destination of that packet here will have a next hop set to the 192.0.2.1. So that'll be the next hop that we advertise via BGP. We say that is the next hop right there. That router right there will drop it. Does everybody understand the logic here of this example here? Not the consequences, not that we're bringing down a site. I mean, that's basically what we're doing. But does everybody understand the logic of preloading the edge routers with a static route to null, preloading the trigger router to redistribute static in? Anytime you redistribute a static in that has a tag of 999, you're going to set the local preference high so that these edge routers prefer it. And then you're going to also you're going to set the next hop so that that next hop matches this one right here, so that these edge routers route this packet to null. So that's the basic idea. The actual trigger is the static route right there, and you only put that on the one router. You put that on the trigger router, that's it. So you go on the trigger router and put this on. The way to test this, you don't need the tags, you don't need the local preference, assuming they're not running the route any other way. You can just test this. A lot of other features you can put on here, like I said, you can set the community so that you don't advertise this out or whatever here. You don't advertise it out to the internet here, but just redistribute static. Then it comes in. Then when the attack is over with and you want to allow normal routing to that attack, well then what you do is you just remove the static route from the trigger router. And as you can see, it's something you can do really easily. It's really easy to automate this, I should say. It's really easy to automate this. You got to just go in, have a script go in, and put in a static route in the trigger router, and it's automatically propagated to all the edge routers. The device is not under attack anymore. Have your script go in, remove the static route, and it's propagated to all the edge routers. The traffic flows normally. This isn't Cisco specific. You could do this with any other vendor's equipment. You could do it with a Linux box running Zebra if you wanted. All right, and have it advertise this route out to your edge routers there. Okay, so this is destination based. Okay, so this is destination based here. I recommend you play around with this. You'll see this in the workbook once or twice, different variants of this here. The other option is to do source-based filtering. So now what we're trying to do is we know that the particular IP address or a particular IP address range keeps scanning our network, and we want to drop it right at the edge. Okay, so we want to drop that traffic right at the edge. It keeps scanning our network here. Okay, so what we do is we configure loose unicast reverse path forwarding. So this will be on all our interfaces here. And then everything else is exactly the same. Nothing else changes except our static route. Our static route now is the source of the attack. So if the source of the attack is, if I'm getting attacked from IP addresses on this network right here, so if IP addresses on that network right there are attacking my servers, okay, what I can do is put a static route on the trigger router. So I put a static route on the trigger router to this. So I say IP route. So IP route 210.50.0, 255, 255, 255, 255. So null 0 there, and specify my tag 999 here. Now what's going to happen is this is going to get redistributed into BGP. It's passed into BGP here through this command here, redistribute static route map. It matches the tag, so it comes in. We set the local preference high, so we prefer it. We do a set IP next hop. So now the next hop for this is via 192.0.2.1. So that's the next hop. So this is the route that goes out. The route that we send out is this right here, the next hop. When the edge router gets it, that means that this packet is essentially routed to null, because the next hop is routed to null. So when the update comes in, it's in our BGP table. We do a show IP BGP, and it shows up 210.50.0. Next hop 192.0.2.1. Well, when the packet when the packet comes in with that source, the URPF does a check on it, and because the the interface essentially we would forward it to is null zero, the packet gets dropped. Okay, so the logic is the same. The logic is exactly the same between destination and source. The trigger router doesn't do anything different. Those are the exact configs. Those are the exact configs that you would use here. These configs right here. I can post these up tomorrow with the post these configs up tomorrow, so you'll have them in regular text file format when I post up those internet access configs there. All right, but this is the basic. This is how we're going to do it here. From the trigger router's perspective, nothing changes. The best way to set this up in the real world is to set it up to do destination-based and source-based, because source-based is just one additional command. You're just going on and putting on IP verify unicast source reachable via any. Okay, you're just putting that on. Then the way you determine if it's going to be a destination that you're going to black hole or a source, it's your static route. Does your static route point to the source of the attack, or does it point it to the destination of the attack? What do you want to do? If I just want to block the source, if it's coming from one IP address, well, I'll do source-based filtering. It's just coming from one IP address. If it's coming from 100 IP addresses and it's a DOS attack, well, I'm going to do destination-based. I'm just going to black hole that server while they're doing this DOS attack there. Okay. All right, so I'll post these configs tomorrow with the I'll post these configs tomorrow with the internet access configurations. So if you guys want to play around with it, I would definitely recommend playing around with it. There's a couple white papers if you search Google for remotely triggered black hole filtering. Some of them are really extremely long, like 50 pages. But this is the idea of it. This is the basic idea. You can get into variants, like I said. You could do things like come out with different next hops for different routers. Maybe this one is .2. This one, I mean 192.0.2.2. This one is .1, and this one's .3. So then I can determine where I filter at. If I just need to filter on one router, I'll put my static route and set the next hop to .2. So if I set it to .2, it only affects this router right there. You can do all kinds of crazy variants of this. Preparing for the service provider exam, I would just know the basic kind of stuff. All right. Someone had a question here. We relate to lab, but the ISP is actually implemented in the real world. I mean, the solution seems to be on a per event basis. If you work at a large scale ISP, you'll have people that do nothing but help mitigate attacks. I mean, one ISP I worked at, the guy's job all day long was to fine-tune BGP. All he did all day long was to fine-tune BGP to ensure that optimal routing occurred through the network. Yeah, you'll have in big ISPs. You got, what can you do? Let's say you've got an OC3. You've got you got 3,000 clients, but yet 4 or 5 of them under attack. Each attack is taking up 10 megs. I mean, what can you do? Can you take up, a third of your bandwidth? That's costing you probably, $50,000 a month or $40,000 a month. So I mean, there's nothing. Sometimes you don't have any choice but to just black hole them, and you're going to have to get it because they will eventually stop. I mean, they're not these zombie PCs that usually this comes from. They eventually get fixed, so they're not going to be like this forever. And maybe 3 or 4 days, maybe a week. But it'll eventually start to weaken down. You may, from real world perspective, you may see a down service that kick up, die down, and then kick back up again once they get more machines under control. All right, but eventually, the PCs will theoretically eventually get fixed. These aren't the same PCs that are zombie PCs for 3 or 4 years. Usually, they eventually get fixed there. All right. Okay. So I'll post these configs for these two in text format for you tomorrow. You have the 4 internet access solutions, and you have this config. This is the kind of stuff you need to practice for the lab, that like the internet access. Don't take it for granted that you saw how it worked and you know how it works. Play around with it, configure it, verify it, and you'll definitely help you in your learning process here.